yesterday we described and talked about the 68, 95, 99.7 rule. What's another name for 68, 95, 99.7? Empirical rule. Yeah, good. And we can describe a standard normal distribution using the mean and standard deviation to describe it. Right? Today we're going to talk about normal calculations, and assessing normality will be another day, not today. So, the standard normal distribution is what happens when we standardize. So we're going to put things in, using our z-score, we can standardize it. It's the normal distribution with mean 0 and standard deviation of 1. A standard normal distribution is a normal distribution with a mean of 0 and standard deviation of 1. So again, here's your formula for finding a z-score. It's your x value minus the mean divided by standard deviation. This is population mean, and this is population standard deviation. Before we were looking at the sample. Just side note, this was sample mean. This is population mean. And this, our S sub x, was a sample mean. Sample standard deviation, and this is population standard deviation. That's just kind of a side note, extra plug for you. Just different symbols. Population mean, sample mean. Population standard deviation, sample standard deviation. When we talk about normal curves, we're basing it on the entire population, supposing everything's completely normal. So here's your mean, your standard deviations. I've shown you that several times now. Here's what happens. Because all normal distributions are the same when we standardize, we can find areas under any normal curve from a single table. It's like your percents, your proportions, our areas are under the curve. So table A, grab your textbooks for a second and turn all the way to the back and find table A. Table A, it's T-2, one of those last 5 pages all the way to the back. So, what do? Suppose we want to find the proportion of observations from the standard normal distribution that are less than 0.81. So if I say find z less than 0.81, where does my 0.81 fall? Roughly in here. And I want to know, this table always measures to the left. What do we know here? This is just kind of a way to talk you through it and kind of get you to think. From 0 on left is half of our data, for 50%, right? So I'm a little bit further than that. So when I look it up in the table, I'm finding all of this. So if a z-score of 0.81, we go to our chart, we find 0.8. Across the top, we find 0.1, and we see where they intersect. So that tells me, one second before you get this all written down, that tells me 0.7910 is all of this in here. Sometimes we write it as 79.1% is the area to the left of 0.81. So look at your table. This is a lot larger scale table. See if you can find positive 0.81 in that exact same number. So in this example here, it says find the proportion of observations from the standard normal distribution that are between negative 1.25 and 0.81. Every single time I would tell you to sketch a curve because I think it helps us kind of understand and see what's going on. So here's my rough curve. We know 0's in the middle. I know this is negative 1, negative 2, negative 3. Roughly in here will be negative 1.25. Here's positive 1, positive 2, positive 3, 0.81, somewhere in here. I'm concerned with this in between. When we go to our table to look up like a z-score of 0.81, the z-score always measures to the left of that. So go to your table, find 0.81, which we actually just did. And we said that was 0.7910. 0.7910. So really, like 79% of the data lies to the left of that z-score. But do I want all of this? No, I need to get rid of this part right here. So I look up what's negative 1.25, and I need to subtract that part out. So find your z-score, negative 1.25, so 0.1056. And again, I always try and think through in my head, does this make sense? Is it approximately 10% to the left of there? Yeah. When we were saying 80%, I would be like, no, this is not 80%, so there's something wrong with that. So this is 79%, this is roughly 10%, so off to the side we're going to go 0.7910 minus 0.1056. We subtract 0.6854. 0.6854, or 68.54% of the data lies in between that range. And I can't stress this enough. These numbers here, and all these numbers across here, in the outer column, those are your z-scores. Along the edges, those are your z-scores. And this in here, all of this in here, so make an arrow, make a note, make something. These numbers in there are what I refer to as your area. Sometimes they're referred to as a proportion. And often I refer to them as percents. They all mean the same thing. What's the area under the curve? What's the proportion in between these 2 points? What percent of the data lies in between in this range? Z-scores along the edge, inside all these numbers in here, these are percents or proportions or your area. So how about here? Find the proportion of observations in a normal distribution that are more than 1.53 standard deviations above mean. That is, what proportion of observations in the standard normal distribution are greater than z equals 1.53. So I sketch my rough curve. I know zero's in the middle, and you're going to often see me do this. I'm not going to put in the other marks. I'm like, I know 1.53 is out here somewhere. I'm looking for more than that. And really, that's all the more that I am writing on my chart. It just gives me a visual. What's going to be more than 0.53? Is it going to be more than 50% or less than 50%? Less than 50%, right? This part right here has to be less than 50%. So here's the question. When I find 1.53 in my table, like I said, it always measures to the left. So what's to the left? 0.9370? The curve is always out of 100%, or that's equivalent to 1. So what do we subtract? Yeah. So 0.9370 is to the left, so what's to the right? Take 1 minus that, and that's going to tell me what this is. 0.063 is what's in here. Let me talk to you this way in terms of percents. The whole curve is 100%, or 1. It's all 100%. This part right here is like 93.7% to the left. So if I go 100 minus my 93%, that gives me 6.3% in here, or your 0.063. So either way you label it, you write it, I would be okay with that. When it says proportion, it's really looking for that, but either way, whichever makes more sense to you. You guys try this next one on your own and see what you get. Sketch your curve. Now we start and we work backwards. In a standard normal distribution, 20% of the observations, so when I say 20%, where are we looking? Your percents are inside, right? So sketch your curve. Again and again and again. 20% of the observations are above what value? So I'm looking at my top 20%, right? 20% are above what z-score? But I can't just look up 20% of my table because the table always measures to the left. If I have 20% to the right, how much is to the left? 80%. So I have 0.8000. So when I look at my table, so I come in here and I look as close as possible. Where's my 0.8000? And it's rarely going to be exact, but we find the one it's closest to. So it's in between these two numbers, right? So if I put 0.8000 in there, here I'm actually closest to it. I'm 0.005 away versus 0.0023 away. This is the closest one. So it is at 0.8, carry it up, 0.84 is my z-score. That's it. So it gave me, it's like, well, what's above 20%? Well, my z-score is always measured to the left, so I need to figure out 80% is below. I find 80% inside my table because it's under the curve, it's in here. 0.8000 gives me a z-score of 0.84. 0.8000 is right in there, right? Which one is it closest to? It's closer to this one than it is to that one. So I come up here, and I come over here, and I'm like, it's at 0.84 is my z-score for it. So sometimes I'm not just going to straight up give you the z-score. So if I give you an example like this with Tiger Woods and I give you 304 and 8, is 304 and 8, is that on our chart? Those numbers are huge. So here's what we need to do. We need to first of all express the problem in terms of the observed variable x. In other words, what are we talking about? And I'll walk you through this in a second here. We draw a picture, we perform our calculations, which means we have to either standardize, we usually have to standardize and use table A, and then we write our conclusion. When Tiger Woods hits his driver, the distance the ball travels can be described by N304.8. What's 304 stand for? The mean, and 8 is our standard deviation. What percent of Tiger's drives travel between 305 and 325 yards? Here's my curve. 304 is in the center. We could count, we could figure it all out, but I'm interested in between 305 and 325 yards. I'm interested in this right here. So I sketch my curve. Now I need to do some calculations. Let's take a sidetrack a second and make sure you get this on your paper. So we talked about how to standardize. We take the z-score. To find our z-score, we take x minus the mean divided by standard deviation. Here's a picture, and we're going to keep coming back to this. So to standardize, I can find my z-score with that formula. We sometimes have real-life values, is what I call it, like in this case. I give you these real-life values, and so based on those real-life values, we need to standardize the information so that I can come down here and I can use table A to find my percents or my proportions or my area. And I'll refer to this many times of how we bounce back and forth. So I have my real-life values. In order to figure out what percent of the drives travel between 305 and 325 yards, right now I'm here. I want to find a percent, so what do I have to do? I have to standardize in order to get down here. So let's say when x equals 305, our z value is going to be what? You take your x minus your mean, divide by standard deviation, and the z-score here is, so your z-score is 0.13. So this at 305 has a z-score of 0.13. So I'm just kind of making a note of that. And then I need to find this other z-score too. So then we have when x equals 325, our z-score is 325 minus your mean divided by standard deviation, and that gives us, your z-score is 2.63 here, so here z equals 2.63. So now we use the table, right? From here left, if you look up your z-score at 0.13, how much of the data is to the left of 0.13? 0.5517, let's keep those 4 digits in there. And then at 2.63 standard deviations to the left of there is 0.9957. What's in the middle? We subtract. Gives us 0.4440. So draw your conclusion then. About 44% or 44.4% of Tiger's drives travel between 305 and 325 yards. How about here? In 2008 Wimbledon, in the 2008 Wimbledon tennis tournament, Rafael Nadal averaged 115 miles per hour on his first serves. Assume that the distribution of his first serve speeds is normal with a mean of 115 and a standard deviation of 6 miles per hour. About what proportion of his first serve speeds would you expect to exceed 120 miles per hour? So first of all, we state our question. We're going to let x equal, what are we talking about? The first serve speeds, yeah, in miles per hour. The variable x has a normal distribution with a mean of 115 and a standard deviation of 6. And we want the proportion of first serves with x greater than or equal to 120. What exceeds 120 miles per hour? So I gave you the picture here. This is at 120, so I need to know what is the z-score for 120 so I can figure out this proportion here. So we have our x minus our mean divided by standard deviation. 0.83. Careful. This is our z-score. Z equals 0.83. It's how many standard deviations above the mean. It's not a percent yet. So because this is my z-score, I'm just going to say z equals 0.83 here. How much lies to the left of 0.83? That's how much lies to the left. And if I want to know how much is above that, I go 1 minus 0.7967, and we get 0.2033. So how much is up here? 0.2033 or 20.33%. So what do we conclude? About 20% of Nadal's first serves will travel more than 120 miles per hour. Sweet.